Welcome to Module 16 on simplifying radicals. Right now, make sure you have your notebook out for your notes. Don't forget that note-taking is important because you can use it to reference when you do your problems, and you can use your notes on your quizzes. Turn to a new page, write Module 16, Simplifying Radicals at the top of your paper. Today we're going to be talking about simplifying radical expressions both with an odd and even exponent. We're going to simplify square roots of perfect squares and simplify radicals with two variables. So I want to give you some introduction to simplifying a radical expression. So new topic, simplifying radical expression and introduction. And I want to do it in the context of something that you already know about, which is perfect squares. So for example, almost all of you know that the square root of 4 is 2. I want to break that down for you a little bit farther and talk to you about how pairs of products are perfect squares. So pairs are squares. That's going to help us remember what we need to do here. So I want you to remember that 2 times 2 is 4. Notice how we have a pair of 2's here, and so that's why the square root of 4 is 2. 9 works the same way. 9 is 3 times 3. We have one pair of 3's, which is why the square root of 9 is 3. Square root of 16. 16 is 4 times 4. There's a pair of 4's, and so 4 is the perfect square. Notice that I don't put a square root on it. That would be incorrect. The square root of 16 is just, not 14, is just 4. So I want you to remember how I made these trees, and we're going to use that to help us moving forward. And I also want you to remember the little rhyming thing that I told you, that pairs are your perfect squares. So if I were capable of writing out 36 y's every time, which I am not, it's crazy. Don't forget, new topic, simplifying a radical expression with even exponents. I'm going to write them all out this time. I'm going to do 6 rows of 6 y's for 36. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm going to fill all these in. I would never have you do this in real life. I'm getting ready to teach you a shortcut. Remember, pairs are the perfect squares. So if this were the square root of 4, 4 is 2 times 2. There is a pair of 2's, so that's why the square root of 4 is 2. What I want to think about is how many pairs of y's there are in 36. There's a pair, there's a pair, there's a pair. I'm circling all the pairs. Again, I'm never going to have you do this in real life, I promise. I'm going to teach you a shortcut here in just a second. So now I have circled all the pairs, which means there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 pairs of y's. What that means is the square root of y to the 36 is y to the 18th. Well, let's think about a shortcut. If I want to find pairs and I want to see how many y's there are 36 of them. I circled 18 pairs. Half of 36 is 18. So the shortcut, instead of writing all of these out and circling the pairs, is to just divide by 2. So 36 divided by 2 is 18, and so that becomes y to the 18th. You try this one on your own. You can write out all 14 x's if you want to, or you can try to use the shortcut. Go ahead and do that now. All right, so if you wrote all these out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 1, 2, 3, 4, 5, 6, 7 pairs, and so this is x to the 7th. The shortcut is 14 divided by 2, which is 7, and so the square root of x to the 14th is x to the 7th. We can do this using numbers. And we just sort of treat these separately. It's just that we put our answers together. Almost all of you know that the square root of 49 is 7. That's true because 7 times 7 is 49. There's a pair of 7's. So the square root of 49 is taken care of. But x to the 14th, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 x's. There are 1, 2, 3, 4, 5, 6, 7 x's. So that becomes x to the 7th. It's just a coincidence that this number and this number are the same. That won't always happen. You pause the video and see if you can do this one on your own. You should have started by finding the square root of 25. Almost all of you could have done this without the tree. 5 times 5 is 25, so the square root of 25 is 5. If I look at the 4 y's, there are 2 perfect squares, so it's y squared. By the way, if you hear some noises in the background of my video today, my neighbors are setting off fireworks while I'm making this video, so sorry about the noise. All right, what if the number isn't a perfect square? 50 is not a perfect square. So far, it has sort of seemed silly to write out all these trees when you could do these on your own in your head without all the trees. We do the trees because of this. 50 is not a perfect square. What I'm looking for are the perfect squares that are hidden in 50. So I'm going to make a factor tree, and I always start with 2. 50 divided by 2 is 25. 25 is not divisible by 2, it's not divisible by 3, it is divisible by 5. So notice I'm trying prime numbers. 25 becomes 5 times 5. So what I have is a pair of 5s and I have a single 2. What that means is when I set up my answer, the pairs are the perfect squares. So 5 is the perfect square. The 2 has to stay inside the square root. Now we can do w to the 16th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 1, 2, 3, 4, 5, 6, 7, 8 perfect squares of w's. So that becomes 5w to the 8. The only thing that go inside the radical are things that don't have a pair. Remember, the pairs are the perfect squares. You go ahead and pause the video and try this one on your own. You should have started off with your 45 and made your tree. 45 is not divisible by 2, so we go up to 3. 3 times 15 is 45. 15 is still divisible by 3, so 3 times 3 is 5. I do this in a certain order so that my pairs are together. I have a pair of 3's and a single 5. So if I'm just simplifying the square root of 45, I have a pair of 3's and a single 5. Now for the x's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this will be the last time I write this all out. From now on, I'm going to use the shortcut when I can. 1, 2, 3, 4, 5 pairs of x's. They are all perfect squares, so they go on the outside. There's no single x's left over, so those don't need to go on the inside, and we're done. Now, what if we have odd exponents? The number we take care of the same way. So we're going to do 32. 32 is not a perfect square. It is divisible by 2. 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. So now we're looking for the pairs of 2's. There's a pair and there's a pair. There's one single. So what I have on the outside of my square root is a pair of 2's, another pair of 2's, and a single 2. We're going to clean this up in just a second, but for now we're going to look at our u's. There's 1, 2, 3, 4, 5. That's a u, not a w. There are 1, 2 pairs, so that's u squared. But now there's one single u that goes on the inside of the radical. On the outside or the inside, if there's anything that can be multiplied together, we want to do that. 2 times 2 becomes 4. The u squared comes down, and the square root of 2u comes down, and that's my final answer. You pause the video and try this one on your own. You should have started with your tree if you didn't know the perfect square. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. These are all perfect squares. So on the outside of my radical is 2 times 2. So far, there's nothing to put on the inside. Now let's look at our y's. There's 1, 2, 3, 4, 5. There's 2 pairs of y's, so the perfect squares go on the outside. The single goes on the inside. The only thing we have to do is clean up the 2 times 2, so that becomes 4y squared times the square root of y, and that's my final answer. Now, sometimes you might have more than one variable on the inside. We still treat the number separately, so we're going to make our tree for 28. 2 times 14, 2 times 7, 7 is prime, so we have a pair of 2's and we have a single 7. Notice I have some space in between so that I can start filling in this other stuff. There's only one single x. There's not even enough to make one pair, so the x has to stay on the inside of the radical with the 7. Let's look at our z's. 1, 2, 3, 4, 5. I put a line through my z's so that they don't look like a 2. There are 2 pairs of z's, so z squared goes on the outside, and one single z left over, so that goes on the inside. So my final answer is 2z squared times the square root of 7xz. And that's it. It's fully simplified. You pause the video and try this one on your own. You should have started off with your factor tree. 16 is 2 times 8. 8 is 2 times 4. They're all perfect squares, which is what makes 16 a perfect square. So outside the radical becomes 2 times 2, and there is nothing so far on the inside of the radical. Now let's look at our x's. There's 1, 2, 3, 4, 5, 6, 7. There are 1, 2, 3 pairs, so it's x to the third on the outside and a single x left on the inside. And there's only a single w, no pairs of w's, so it has to stay inside the radical. So my final answer becomes 2 times 2, which is 4, x to the third, times the square root of xw, and that's my final answer. And you're done. Short one on this one. Module 15 was pretty long, so I tried to keep Module 16 short. This video will be available on Haiku if you need to rewatch. You need to go do your practice problems for Module 16 by hitting Continue My Path. Don't forget you'll need to do Modules 1 through 15 if you haven't done so already. Don't forget to use the explanation tab on your ALEKS questions. And don't forget to take Quiz 16 under Assignments. Have a great day.